Let ABCD be a convex quadrilateral with BA not equaling BC. Denote the incircles of triangle ABC and ADC by omega 1 and omega 2 respectively. Suppose that there exists a circle omega tangent to ray BA beyond A and to the ray BC beyond C, which is also tangent to the lines AD and CD. Prove that the common external tangents to omega 1 and omega 2 intersect on omega. So here I labeled the intersection point as point X. Our ultimate goal is to show that X lies on omega. So now let's take a closer look at the diagram to see if we can make any general conjectures. We might want to try looking at the incircles first, because that might tell us something. And if we do, then we see that if T is a tangency point of omega 1, and U is a tangency point of omega 2, which I labeled here, then we conjecture that AT is equal to CU. So how do we prove this conjecture? Well, because we have double incircles here, and we have AT and this incircle, and CU and this incircle, we can try expressing AT and CU in terms of the lengths of the respective triangles. In particular, we have AT is a semi-perimeter of ABC, which is AB plus BC plus CA all over 2, minus the length BC, and CU is equal to the semi-perimeter of ACD, which is AC plus CD plus DA over 2 minus the length AD. And let's try proving that these two are equal. Clearing denominators by multiplying both sides by 2, this ends up becoming AB plus BC plus CA minus 2BC is equal to AC plus CD plus DA minus 2AD. And now we see that the AC's canceled from both sides, so we can ignore that. And BC minus 2BC is just minus BC. And similarly, DA minus 2AD is equal to minus AD. So our condition turns out to be AB minus BC is equal to CD minus AD. And rearranging the conditions gives AB plus AD is equal to BC plus CD. So our conjecture that AT is equal to CU is equivalent to AB plus AD is equal to BC plus CD. So how do we prove this new thing? In order to prove this condition, we first have to recognize that it looks a lot like this theorem called Pareto's theorem, which states that in the quadrilateral with an incircle, we have AB plus CD is equal to BC plus AD. This equation here looks very similar, except now we have AB plus AD instead of AB plus CD. But now we recognize that omega exists, and it is tangent to all four sides of the quadrilateral. So we could try using that to our advantage. Indeed, let's go ahead and try using it. Let's go ahead and label this point here E, this point F, this point G, and this point here H. Those are the tangency points of omega with the sides. Then let's try looking at AB plus AD first. Well, the only other point that's on line AD is point E, so we might want to try adding the length DE to it. Then this becomes AB plus AE. But now we recognize that AE is equal to AG because of equal tangents. So that means that it's AB plus AG, which is just BG. And now we can try using something similar for BC plus CD. We have BC plus CD plus, and in this case DF, is equal to the length BC plus CF, which is BC plus CH, which is BH. But now we recognize that BG is equal to BH. So therefore we know that these two quantities are equal. And we also know that DF is equal to DE. So these two cancel out, and we indeed have AB plus AD is equal to BC plus CD. And therefore our conjecture holds. Now that we know that AT equals CU, we can now recognize something important about the point U. We see that the line BU must intersect the top point of the sin circle. That is the point that is diametrically opposite the point T. Recall this from an earlier video, which I will link inside the description. Either way, let's go ahead and label the opposite point of T prime to be T prime, And now here's where the real fun begins. We can now use a bunch of homotheties. First, we try looking at homothety centered at B, which maps omega to omega 1. This means that if we let V be the bottom point here, because T is the bottom point here, we might want to let V be the bottom point here. So let's go ahead and let that be V. Then a homothety sending omega to omega 1 sends V all the way to point T because the bottom points are mapped to each other. So omega to omega 1 brings V to the point T. Then now let's consider a homothety going from omega 1 to omega 2. Then this brings point T to the bottom point of this circle here, which is just the point diametrically opposite the point U. I'll go ahead and call that point U prime. Then omega 1 to omega 2 sends T to U prime. And finally, we have that. Now let's go consider omega 2 to omega, because that will bring us back to where we started, in a way. Then omega 2 must send this point U prime, to a point on the circle here, because V started on the circle to start with. But now we note that this homothety here is positive, and this is positive, and this is negative. So the composition of all the homotheties is just negative. And since we go back to omega, we recognize that the composition of all of these homotheties is just equal to a reflection about the center of omega. Therefore, if V prime is a top point of omega, let's go ahead and call this V prime, then that means that we have U prime gets mapped to V prime. And this means that D, U prime, and V prime are collinear. Now that we know that D, U prime, and V prime are collinear, we can try drawing a line connecting them. And we definitely conjecture that it passes through T as well. Actually, this is a consequence of the same result we used to show that B, T prime, and U are collinear. Because U prime is a top point, and again, as per the result I made in the video linked in the description, we have D, U prime, and T are collinear. Therefore, this implies that T, U prime, and V prime are collinear. Similarly, since T prime is sent by a homothety centered at B, mapping omega 1 to omega 2, it gets sent to the point V prime because top points get mapped to top points. We have that B, T prime, U, and V prime are collinear. But we won't need the B part, because now we know that TU prime and T prime U intersect at point V prime. However, the intersection of the top points of each circle and the intersection of the bottom points of each circle is just the center of homothety. So therefore, V prime is the center of a homothety sending omega 1 to omega 2. However, because X is the intersection of the external tangents, X must be this point. Therefore, X must equal V prime, and V prime clearly lies on omega by definition because V is the bottom point of omega, and therefore X lies on omega, and we have solved the problem. The main technique that we used to solve this video was the power of using homotheties and their compositions to end up getting this result. So thank you so much for watching this video. Please subscribe if you'd like to see more.